These are the frequently asked questions for pre-calculus for section 3.1 day 2, starting with number 49. In exercises 45 to 50, graph the function and analyze it for domain, range, continuity, increasing or decreasing behavior, symmetry, boundedness, extrema, asymptotes, and end behavior. So for number 49, things that we want to pay particular attention to. Here's our upper limit, and that's a 5 up there. So I know that I have asymptotes at y equals 0, and y equals 5. So those are my lower and upper limits here. And then what we would want to do is figure out, what this graph is going to look like. So that's a matter of, just like we did in class, finding really two things. We want to put a 0 in for x and see what we get. Well, if we put a 0 in for x, anything to the 0 power is 1. So on the bottom we'll have 1 plus 4 times 1, which is 5. And 5 divided by 5 would give us 1. So there is a point on our graph. And then, as I explained in class, we always want to find that inflection point. That's always something that's really important. And how we get that is by taking c, that upper limit, and dividing that by 2. So that gives us 5 halves, or 2.5. So what we want to know is, what's the x value that will give us that 2.5 inflection point that we need? Well, that means we need to work backwards and figure out what x is. So 2.5 is going to equal 5 over 1 plus 4 times e to the negative 2x. So first thing we would do is slap a 1 under here and cross multiply. I wouldn't even bother changing that into 5 halves to cross multiply. It's not going to make any difference. So when we do that, we get 2.5 times 1 plus 4 e to the negative 2x equals 5. Then we could divide both sides by 2.5 and get 1 plus 4 e to the negative 2x equals 2. As I said before, it really wouldn't make any difference if we used 5 halves here or 2.5 over 1. Then we would subtract 1 from both sides, divide by 4, and to get rid of e, we take the natural log of both sides. So over here we have our inverses, and over on the right hand side we'll have the natural log of 1/4, or 0.25, and then we will divide by negative 2. So x will equal the natural log of 0.25, all divided by negative 2. And that comes out to 0.693. So our inflection point, or point of inflection, is going to be at 0.693, 2.5. So we'll go back up and get that graphed. .693, so a little more than halfway between 0 and 1, and then up 2.5. Now, like we talked about in class, the graph is always symmetric about that inflection point. So what you want to do is think, okay, if I go from here to here, I want to do about that same thing here. And that will get us about right there. So, without a graphic calculator, we get a pretty good look at what this graph is going to do just by using symmetry. So now we had all of those questions that we had to answer involving all of the behaviors. So domain and range and continuity and all of that good stuff. So domain. We know this is going to go right and left forever, so that's going to be negative infinity to infinity. Our range, well, we definitely have those two asymptotes at 0 and 5, so we're not going to include 0 and 5, but everything in between that is the range. This is definitely continuous. We would never lift our pencil as we graph that green graph. It would always be consistently on the paper, and it is always increasing. It starts low and goes high. So that interval is negative infinity to infinity. Now, it said symmetry, And no, it's not even, and no, it's not odd, but boy, we better start to recognize that it is symmetric about the inflection point. And our inflection point was 0.693 and 2.5, because that is going to save us so much work as far as this graph goes. It is bounded below by that asymptote y equals 0, and it is bounded above by y equals 5. So we have just told them what the two asymptotes are. We have two horizontal asymptotes. And those are at y equals 0 and y equals 5. We do not have any extrema here, so no local or relative extrema. And we have the end behavior to talk about. So let me erase this little piece down here so that I have some room to do end behavior with you here. So end behavior is back to talking about, oops, I'm going to stop. The limit as x approaches negative infinity, and this one was f of x. And the limit, I made myself some room here, limit as x approaches infinity of f of x. Well, as we go to the left forever, our graph is going to approach 0. It's getting closer and closer to that. And as we go to the right forever, it's going to approach that 5, that upper limit. So really good example of a logistical function and all of the behaviors that we know about that graph. It never had to use a calculator, which is the best news of all, because we know in calc next year, not going to be allowed to. 51 says, using the mid-year data in table 3.7 and assuming the growth is exponential, when did the population of Austin surpass 800,000? All right, so with number 51, I notice here we're going from 1990 to 2000, so that means they had that original 465,622. And then, because it's exponential, they multiplied that by some x value, but they didn't do it just once because they had 10 years to span here. So every year they multiplied it by another x that they had. And again, the x didn't change because this was consistent growth because it was exponential. And that came out to be 656,562. So what we're going to have to do is divide both sides by 465,622. And then we're going to have to take the 10th root. And you'd punch that in as 10 math, and then you'll find that generic root button that you have under there. And then I would use parentheses for the 656,562 divided by 465,622, parentheses. And our x will come out to, because we're talking about a 10th root, we should think plus or minus, but in this situation, since it's population growth, we would know that we would only use the positive here. So there is the number that we needed for the model. That's our basic y equals a times b to the x model. So we are talking about population, and the initial amount, 465,622, we found, pardon me, we found what we're doing for b, our base, and that's going to be our 1.035. And then we could just use t for time in years. So let's see what they wanted. We've got our model. And the second part of this is, when did the population surpass 800,000 persons? So we would want to know, put all my zeros on there. And this, again, I would love to do this with logarithms, but at this point the book had us just using the graphic calculator to figure out that intersection. So, you know what, I'll go ahead and put put this into the calculator for you because maybe that was the issue. Maybe you just had trouble getting all of this in here. So I'm going to pause this for a second and get that in. You can see that I went ahead and entered our equation, 465,622 times 1.035 to the x. And we wanted to see when that was 800,000. So pretty obviously we're going to have to change our window here. And it was in years, I don't know, maybe I'll use 25 years to start off with, 0 to 25. And then my y min, I'll do 0, and we want 800,000, so maybe I'll go with 1 million. And graph. So there is the exponential model. You can see that coming up. And it is definitely increasing because we have 1.035, which is greater than 1. And there is our 800,000, and then we have second trace, number 5, the intersection, and enter 3 times. And Blinky, as always, incredibly helpful. 15.733 years. So this started in 1990, and I would definitely round this up to 16. So in this situation, it's going to be sometime in 2006. Sometime 2006. Now, you had also asked for the next one, which really uses the exact same table. It's just using the different numbers because it is about Columbus. So for Columbus, we'd go through the same process of figuring out what the x value is. And the x value, again, is our base, so that's really important. So 632,910. For 10 years, it grew at some rate. And that gave us 711,265. Now we're going to do the same thing. We're going to divide, and then we're going to take the 10th root. So what we're really looking for our base is the 10th root of 711,265 divided by 632,910. And that comes out to be 1.011. Now, normally we'd go 3 decimal places, but it kind of bothered me that there was a 7 in that next position. We found that when you have large population numbers, a small difference, like a 10,000th position, can make a difference, big difference actually, in your numbers. So this time I went ahead and went with the 4 decimal places just to make sure. Because again, in the end, we want 3 decimal places, but I don't want a rounding error because I chose to do 3 decimal places. So now, we need to know 800,000. And when does that equal our 632,910 times 1.0117 to the t? So once again, this is a matter of putting it into the calculator and finding the intersection. So I'm going to go ahead and pause this and punch that equation in. All right, you can see that I have that in as my y sub 3 now. What I'm going to do next is I'm going to go ahead and hit enter when I'm on the equals for that first graph because I don't want that one to graph anymore. The other two you can see are still highlighted, the equal sign right behind the y sub 2 and the y sub 3. I just want to focus on what's going to be the red and the black here. And I am just going to hit graph again in the hopes that this same domain and range are going to work just fine. And it looks like everything's going to be okay. We can still find that intersection. So second trace, number 5, enter 3 times. And it tells us that we are looking at 20.141 years. So we definitely can round that to 20 years, and then this one started in 1990 as well. So 1990 plus 20 years would put us in 2010. So sometime in 2010 is when that would happen. Now, the reason I didn't clear out that first graph for this is because of 53. It says using that data again and assuming that the growth is exponential, when were the populations of Austin and Columbus equal? So now, if I can go back to my graph, I will re-highlight this and I will unhighlight the 800,000, or you could even clear that one. I mean, we don't need that one anymore. And then hit graph. So now I'm looking at blue and black, and I want to know when are those two going to be the same. So this one gives us that first population that we were looking at. And the next one is Columbus, Ohio. And as soon as this is done graphing, we can find the intersection. So second trace, number 5, bing, bang, boom. And it says 13.481 years later. Now, this is the reason that I'm keeping those decimals there. With the 13.481, we really should be thinking this is about 13.5 years later. So if we take 1990 and we add that 13 to this, we're going to get 2003. But we can be a little more specific than that because remember, population is all about that July 1st cutoff. So if we know that we're going to be using a half a year, we could go ahead and say we know that it's going to be towards the end of 2003. So the end of 2003. All right, so now we've got the population growth out of the way with the exponential models. But this one is a population growth with our logistical model. So using 20th century U.S. Census data, the population of Ohio can be modeled logistically. We have P of t equals 12.79 over 1 plus 2.402e to the negative, oh my goodness, 0.0309x. Ouch, that's small. Where P is the population in millions, that's important. And T is the number of years since April 1st, 1900. There's another important piece of information. Based on this model, when was the population of Ohio 10 million? So here's what I really want to know. Since it's already in millions, when is that going to be 10? I don't know about you, but I don't want to put that into the graphing calculator. I just don't. I would much rather solve this using logarithms. So I'd slap a 1 under here and do a little cross multiplying. And then we could go ahead and divide both sides by 10. And of course, when you divide by 10, all you're really doing is moving the decimal place 1 position over. All right, next up, we would subtract a 1 from both sides. Then we would divide by 2.402. And we would have e to the negative 0.0309x equals 0.279 divided by 2.402. Notice I'm not punching that in at this point because I want an exact answer. And the way that I gain access to that x is by getting rid of that base of e by taking the natural logarithm of both sides. These will cancel each other out because they are inverses of one another. And we'll have the natural log of 0.279 over 2.402. And then what we need to do is divide both sides by negative 0.0309. And we do that, and it comes out to approximately 69.671. So now we think, okay, this was all about years again. And if we go back to the original, we see that this started in 1900. So we need to add our 69.671. And that, of course, is going to be 1969. But the reason I kept that decimal again is to show you, you know, it's going to be late in 1969 because we're more than halfway through that year. So late in 1969. So that was one of the things we talked about in the lesson today, was keeping track of, you know, are we talking about census years for population? Are we talking about fiscal year as in business? All of those things are important differences when you're actually doing this in the real world. 56, it says, using 20th century U.S. Census data, the population of New York State can be modeled by our nice little logistical equation right here. And it says P is population in millions, and T is the number of years since 1800. Based on this model, what was the population of New York in 1850? Well, 1850 minus 1800 is 50. So what we want to know is, what do you get if you plop a 50 in there for your T value? And you're just going to have to be really careful about punching this in. I mean, when I did it, I just went ahead and did this once, but you're going to need double parentheses because you have to get that power in there times 50. You know, that's going to be our negative 0.035005 times 50. You certainly could do it in pieces if you'd want to, but I think if you're careful and you use double parentheses here, you can get the answer for A. What was the population in 1850? And that was 1.79455756.9. But remember, this was in millions, and millions gives us 6 decimal places. So 1, 2, 3, 4, 5, 6. That's where our real decimal would go. 179,455. And we would round up to 8. So 1,794,558 people for A. For B, what will New York State's population be in 2015? Well, 2015 minus 1,800 is really asking us to figure out 215 years later, how many people are there? We did for part A, we're going to have to very carefully punch in a 215 as part of this power that we see up here. And when we do that, we will get 19.27273707. And again, we want to work this in millions, so that's 6 decimal places. 1, 2, 3, 4, 5, 6. So this time we wouldn't need to round up because we have a 0 in the next position. So 19272737, 19,272,737 people. And then part C, what is New York's maximum sustainable population, the limit to its growth? How many people can it support? That comes from C, our upper limit, 19.875. But again, that is in millions. So 19.875 in millions, moving that decimal 1, 2, 3, 4, 5, 6 positions, we would need some placeholders of zeros here. So 19,875,000 people. So this one is a matter of making sure that you understand what's going on in that logistical equation. 58, we have carbon dating. The amount C in grams of carbon-14 present in a certain substance after T years is given by that little monster. And A says, what was the initial amount of carbon-14 present? You have a couple of choices. If you're struggling with this one, then put a 0 in for T. You're going to find anything to the 0 power is 1, and you're going to get 20. But hopefully, if you think this way, y equals a times b to the x, you realize a is always the initial amount, and you can just look up there and say, well, it's going to be 20. B says, how much is left after 10,400 years? Well, that's T. That's time. So what we have to do is 20 times e to the negative 0.0001216 times 10,400, which, yeah, again, it's a monster. You just have to be really careful when you're punching it in. If you didn't get the right answer, you might want to do the e to the power first, follow the order of operations, get that answer, and then multiply it times 20. So this comes out to be 5.6468184112. So the grams of carbon, 5.647 grams. And then the second part of B says, when will the amount left be 10 grams? I thought this was kind of weird. I thought maybe they should have made a part C to this because this is a different question. We want to know, when is this 10? So we're going backwards here to figure out what E is. And with this one, you could just use your graphing calculator and do y sub 1 as 20 times e to the negative 0.0001216t. On the calculator it'll be x. And then y sub 2 is 10. But here's another one where I just think it's so much faster and easier just to do it by hand. So if we divide both sides by 20, we get 1/2 equals e to the negative 0.0011216. T, 0.0001216t. And then we take natural log on both sides, and since we're already working with decimals, we might as well go ahead and change that. Here, those are going to cancel each other out because they're inverses of each other. And then we would just divide by negative 0.00011216. And that will get us T. So natural log of 0.5 divided by negative 0.0001216. And that is going to be 5700.224 years. So approximately 5,700 years with that decay model. Next up, number 64. For x is greater than 0, which of the following is true? All right, so what we want to do is think, if our x here, which in all of these cases is the power, if it's greater than 0, which of these is actually going to make sense? And in A, we're saying 3 and 4 to the same power, but it has to be positive here. So 3 to the first has to be greater than 4 to the first. Well, right away, we could see that that one's not true. You know, all we had to do was try one number there. B, we have 7 to the x is greater than 5 to the x. And if you should be thinking right away, well, of course that's going to be true. If they're both 1s, that's going to be true. If they're both 5,000, that's going to be true because you're starting with a bigger base. So this is B. Why not C? Because those are fractions. And when you raise fractions to a power, they get smaller faster. And the same thing with D. This is really 1/9 to the x and 1/8 to the x. And then in E, they have decimals, but again, those are really fractions between 0 and 1, 17 100ths and 32 100ths. So B is the one that's going to be true. 65 says graph each function and then analyze like crazy. Domain, range, increasing or decreasing behavior, boundedness, extrema, asymptotes, and end behavior. All right, so for 65, graph it. Yeah, let's grab a graphing calculator and let's take a peek at x times e to the x. So hopefully this won't take too long. Otherwise, if it does, I will have to pause it. So we will have x times e to the x. All right, window. I don't know, we'll try zoom 6. Take a peek. See what we see. Pretty good window. You know, we can see what's going on here, and we could use the table feature to get some of those points over here. So we have 0, 0. I'm actually going to change that table so I can see some of the negatives here. This equation. There we go. So coming back over here, we have that 0, 0 piece. And the hard part about this is because we have to use a calculator for those local maxes and local mins, we're probably not going to be able to see what they want us to see here, which is what's happening to E. But let me get a few more points on here. Now, one of the other things we would want to take a look at is whether or not we can get back to positives. So as we keep going with this table, we see here that we're getting closer and closer to 0. But really the only place that we had that x-intercept is going to be at x equals 0. So let me go back and set this table so that when we look at the next one, everything's not all weird. All right. So now we have to answer their questions. And that's going to be all of that good stuff that we analyze. All right, so far so good. So the domain is going to be all rails. We don't have any x's that we did not put in, so negative infinity to infinity. But here's the part where I'm guessing you would have to use the calculator and find the local min here, and you aren't probably going to recognize that as negative 1 over e. But hopefully you would see that you have negative 1 when you find this. It'll say negative 1 and then you'll have a nasty decimal. So then you think, okay, since this had e in it, maybe there's something special about that point. So if you take negative 1 and you put it back up in here for x, you're going to see that this is negative e to the negative 1. Well, negative e to the negative 1 is really a negative 1 over e. And so that's where they're getting that information from for the range. So like I said, kind of a little trick move on their part. So for our range, we are definitely including that negative 1 over e and going on to infinity forever. Now, we do have a decreasing and increasing portion in this graph. So from here to here, we are decreasing. This is getting really super close to 0, but then it pulls away until we get down to that negative 1 for our x's. So this is decreasing from negative infinity to negative 1. And then, of course, the rest of the graph is the increasing portion. So negative 1 to infinity. And then we are bounded below. We did have a lowest point. And that lowest point is going to be negative 1 over e. That is our lowest y value. We do have a local min. And again, that's at negative 1 over e. And then our asymptote is y equals 0. It was approaching that asymptote when we went through there. And the limit as x approaches negative infinity of f of x, and the limit as x approaches infinity of f of x. Well, as we go to the left forever, that's where it's approaching 0. And as we go to the right forever, this is going on forever. It's going up. So that's going to be infinite. Now, like I said, if you don't recognize negative 1 over e, and instead of that, let me punch that in real quick, you had negative 1 divided by e, you would have gotten negative 0.368 with rounding. And that would have been appropriate at this point for you because we just haven't had enough experience with e yet that we would know what's going on there. Now this one, they're trying to hide something here. They didn't simplify that negative power here on the e. And that's a reciprocal. So we should recognize that what they're really asking us for there is 1 over x times e to the x. So they didn't want us to see that for some reason. And again, Probably because they didn't want you to recognize that this is really hyperbolic. I mean, we are doing division here in order to see what's going on. So with this one, I'm going to be really generic here. You could punch it into the calculator and find that's what your graph looks like. And then once you have that in there, you can go through and talk, all right, domain. There's a break here. And that break is an asymptote at 0. And I think it's pretty obvious here that one of our asymptotes is going to be 0. So our domain is negative infinity to 0, union with 0 to infinity. And that's going to be our asymptote there, actually our vertical asymptote. And then range, this is where I hope that you did recognize your negative 2.718 for this one, because this point right here is giving us a negative E value, a negative 2.718. So if you did your local max here, hopefully you would recognize that as you go through it. And then, of course, we do have horizontal asymptote right here at y equals 0. So our range is from negative infinity to negative E. If you didn't recognize the E, you probably wrote negative 2.718. Oh, and I do want to include that point. That is my highest point there. And then we go to 0 to infinity. There's a couple of y's right here that we are not using, and that's what we want to make sure that we have out of there. This does not cross ever the x-axis, so no intercepts. And we do have increasing and decreasing going on here. So our increasing is from negative infinity to negative 1 for the x's, because that negative 1 is what gives us that negative E. That actually, like I said, I really hope that you recognize that when you went to find that local max, negative 1 and negative 2.718. Blah, blah, blah. Decreasing. Well, it's decreasing for the other pieces, which would be from negative 1 to 0, the x values, and then 0 to infinity. So those were decreasing. It's not bounded. Not bounded above, not bounded below. We did have that local max. So there's our extrema at negative 1, negative E. And then we did have asymptotes. It just so happened that they were the x and y axis. So x equals 0 and y equals 0. And we definitely can describe that end behavior. And this was g of x. All right, so as we go to the left forever, this graph is going to go down. So that's negative infinity. And as we go to the right forever, this graph is approaching 0. That was one of the asymptotes that we had over there. So a couple of unique looks that we see to those graphs. Then, 67 says, writing to learn. Table 3.8 gives function values for y equals f of x and y equals g of x. Also, 3 different graphs are shown. So what they want us to do is take a look at what f of x is and g of x is, and then determine what we have going on here. So the first thing that I'm looking at is there a constant difference between either one of these sets of data between each of the points? Because that's the only way I'm going to get a line, is if that is a constant difference between the two. And it is not. So while I'm checking that out, I notice this seems to be going down, but not as fast anymore as we go higher in our x values. And as I look at that, I'm making sure that these are always going by the same interval. So that's always going by an x increase of 0.5. And g of x, well, this one seems to be going down a lot faster. You know, look at the difference between 2.44 and 0.71. So I'm going to kind of label that as the faster decrease there. So A says which curve of those shown in the graph most closely resembles the graph of y equals f of x. Well, I know it's not this one. And I do know that it's not going down as fast as the other one is, so it has to be y sub 1. So it's y sub 1 because both of them are not linear. But the reason that y sub 1 works is because it is decreasing less rapidly as our x values increase. So as x increases. And then B says which curve most closely represents g of x. Well, again, we already know it's not linear, so it's going to have to be y sub 3. So for B, it's y sub 3 because as x increases, g of x decreases more and more rapidly. So just looking at the tables and then interpreting what's going on with those graphs. Now, if you asked about the next set of problems here, it was usually because you must have missed something in the instructions. There's a lot to keep track of here. So this one says let f of x equal 2 to the x. Sounds good. Sounds pretty doggone basic there. That's our most basic exponential growth function. Explain why the graph of f of ax plus b can be obtained by graphing one transformation to the graph of y equals c to the x for an appropriate value of c. And what is c? Oh my goodness, look at all of that. So they're saying if we take 2 to the ax plus b, how could we relate all of this to the a, b, and c business that they have up here? Well, first, if it's just supposed to be 2 to the x, I really want to know how is that base all split up. And I remember that this must have come from 2 to the ax times 2 to the b, because there's addition taking place there. So if I break that apart so that I can actually see a power, I probably want to write it as 2 to the b times 2 to the a raised to the x power, because now that looks just like our y equals a times b to the x when I do that. So what does that mean? They wanted to know what c to the x should be, and they asked us about c. Well, this already has the power of x, so c would have to be 2 to the a. That's the way it would have to work in order for us to see that it's being raised to a power. Because notice they wanted y equals c to the x. What's being raised to that power? That has to be the base. So that's what we would want to do. Now, the book is going to explain this through vertical stretch factors and all of that good stuff. So when it says explain why the graph of f of ax plus b can be obtained by applying one transformation to the graph of y equals c to the x for an approximate value of c. And what is c? We have c as 2 to the a. So if we think about what's the rest of this going to do, you know, what will happen if we raise that to the x power and then we add b? Well, our vertical stretch here is going to be 2 to the b. So vertical stretch factor 2 to the b, because that's the other piece we haven't talked about yet. We talked about the base. This is your base. That has to be your c value, and it has to be raised to the x power. That was a limitation they gave us. But that 2 to the b would be an addition to that, and that would be multiplied out in front. So that's going to be our vertical stretch factor, 2 to the b. Then 69 and 72, again, lots of instructions here. Refer to the expression f of abc equals a times b to the c. That's really important. Don't lose track of that. For example, if A is 2, B is 3, and C is x, the expression is f of 2, 3x equals 2 times 3 to the x. They're just using substitution there for an exponential function. So for 70, it says if B equals x. So if B equals x, all right. Well, if B equals x, then that's going to make this linear. If B equals x, then this has to be a linear situation. Now, why do I say that? Take a look right there. They're saying this is A times, if B is x, x to the c, right there. And so we know it's going to be linear, which means that it has to have a power of 1. So that means that our power, or our exponent here, has to be 1. And in order for it to state the conditions on A and C under which the expression is a decreasing linear function, well, to be linear, we know we have a power of 1. To be decreasing, A would be our slope. So if this is going to be decreasing, A has to be less than 0. So to meet their conditions, where it's going to be a line, that would mean we'll have B equal x, and that has to be linear. In order for that to be linear, our C value here has to be a 1. And then we had to make sure that it was decreasing. So A has to be less than 0. All right, next piece, number 71. Let me see if I can fit that on here as well. So for 71, it says if C equals x. So now they're saying we had this, and this is going to become A times B to the x. Okay, well, this is exponential. That's what this is. And it says they want this to be an increasing exponential function. So if C equals x, state the conditions on A and B under which the expression is an increasing exponential function. There's two ways that can happen. It could look like this and be our exponential growth. Or it could look like this and be increasing. So we think, all right, if it's A times B to the x, how do you get this exponential growth? Well, you get it if A is positive, so A is greater than 0, and if B is greater than 1, because that gives you the growth. Now, here's the other situation where it's increasing. Well, where do we get that from? Well, first of all, this is a reflection of this situation. So you think, okay, well, how do you reflect below the x-axis? Oh, it has to be a negative for A. So A would have to be less than 0. And now, how would we get this to look decreasing like it is? Well, to be decreasing, it has to be a fraction between 0 and 1. So these are a couple of really good challenge problems here at the end to make us start thinking about the role of each of the letters in all of the equations that we're working with.